In this lecture, I'm going to give an overview of sound waves, which are the basis for the study of acoustics. Acoustics deals with the way sound waves propagate and are intercepted by our senses. Acoustics can explain why some sounds seem nice to us, while others are unpleasant. Acoustics can deal with optimizing a listener's experience in a large concert hall and how to design musical instruments. Unlike electromagnetic waves, sound waves can't travel without some kind of medium. Often this medium is air. So let's consider how a sound wave distorts air to propagate through space. The top half of the screen, I've drawn some air molecules more or less evenly distributed. When a sound wave passes through these air molecules, they will become expanded and compressed. So this is a type of pressure wave. We're creating differences in pressure. So at the troughs, we'll have more spread out air molecules. And then at the crests, which are areas of compression, we'll have air molecules that have been squashed together. And then we'll see areas where the air is spread out again. And then we'll see another area of compression. And you can see the periodic nature of this wave emerging. Just like the other kinds of waves we've discussed, a sound wave can be represented graphically. We'll have to change our axes to represent the fact that we're dealing with changes in pressure. The pressure is oscillating, so we'll call the y-axis the pressure axis, and the x-axis can be either the distance axis or the time axis. In this case, I'll just call it the time axis. This means that we're considering the pressure at a single point in space over time. Let's say that we're sitting in your bedroom considering this. So our equilibrium pressure will just be atmospheric pressure, which is 1 atmosphere, 1 atm. And then we'll have some range of oscillation like this. We'll start at the origin at 1 atm at time 0. And then you'll see oscillation like this, which means that the pressure is increasing and decreasing. When you have high pressure, this is a point of compression, and when you have a point like this, you see just regular atmospheric pressure, and this trough here is where you have the lowest pressure. Again, we can measure the period, the length of time for one oscillation, which would be represented from here to here. The period is represented by the variable capital T. For a sound wave, the shorter the period is, the higher the frequency, as with any wave, but this is significant with a sound wave because higher frequency means higher pitch. So you would hear something that's more like this versus that. A louder sound just means higher intensity, which is a measure of how much energy is being transported by the wave at a time. This would be a measure of how great the amplitude is, which is this distance here. The change in pressure increased from atmospheric pressure, which is the same as the greatest decrease you experience. These fluctuations in pressure are what cause your eardrum to vibrate and create the sensation of sound.